Killpack, and he's coming from Princeton School of Music. He's a graduate student there. This is his first time at CogMIR. Welcome.
Thank you. And so yes, brief biographical note, I'm a musicology PhD student, and as quintessential for the PhD experience, after my PhD exams I grew heavily disillusioned with the field and started teaching myself machine learning. And here are some of my results, which may or may not be interesting. We'll see. So let's begin. Since their popularization in 2003 by David Bly, topic modeling techniques have enjoyed widespread use on account of their applicability to finding human intelligible topics in both unstructured text and image data. A minor amount of work has been carried out in applying topic modeling to music, with very promising results, yielding both significant predictive power and usefulness for human understanding, such as Diane Hughes' identification that LDA can be used to identify musical keys when trained on untransposed pitches, or the work of Matthias Malk and others to identify harmonic topics, such as dominant seventh chords, topic versus natural minor chords, and they tracked their evolution over time. These works, however, focus on using musical primitives, such as notes and chords, as a natural analog to words. In this paper, I will advance a new method of tokenization designed to create topics from both chords and chord progressions, drawing on recent results from music theory and music cognition. The result is a set of topics that, although produced without encoding a significant amount of musical process into the model other than chord transcriptions, provide significant insight into musical style rather than just musical syntax, guided by the overarching question: what musical features have the property such that their probabilistic distribution is a telling element of a musical style? We'll begin with a brief overview of the math behind LDA. So the basic intuition is that given a document, each word in the document is generated by topics, where topics are a distribution among words. And you can see on the left, these topics are probability of certain words that tend to be semantically coherent, co-occurring. And this is called Dirichlet allocation because we use Dirichlet priors for everything, which generate the probability vectors for each topic and for each document's distribution among the topics. And this is a real-life example of some topics from a 2012 paper by David Bly. You can see these are quite semantically coherent despite not encoding any information into the model other than just word co-occurrence. So now I will draw from some work of music theorists who, although they're trying to create theories meant for humans to understand music, actually give some very interesting statistical insights into how music works. And I will compare these with how text works. So pop rock specifically has not enjoyed much theorizing by music theorists until the 1990s and was traditionally theorized as either too incoherent or just not part of the realm of what real music theorists would study. But starting with Walter Everett in the 1990s, people have been theorizing how pop rock works. And Walter Everett began by rationalizing pop rock chord progressions in terms of classical chord progressions, identifying them not as just one set of chord progressions, but multiple sets, different micro-languages or micro-styles lying on a continuum from more quote-unquote conservative diatonic-rooted harmonies to those that are major chords or power chords rooted on the minor pentatonic scale, such as metal music. Nicole Biamonte has introduced a similar theory in which pop rock chord progressions can be seen as elaborating or underlying functions. So what might be a typical 1-4-5-1 progression in classical music or the Beatles can be realized with a different style as a 1-flat-6, flat-7 one, the same tonic, subdominant, dominant impulse. And in identifying these sets of progressions that can fulfill the same function, she creates a typology of chord progression styles and identifies a lot of recurrent patterns, such as the 1-flat-6, flat-7, 1, things that begin and end on the same chord and can take place over multiple bar units. And these units, which take place in these styles, or micro-languages, I will use as the basis for a tokenization system from chords to chords progressions. In fact, some corpus studies confirm this intuition that there are multiple micro-styles under pop and rock instead of a monolithic music theory. A corpus study by Temperley and Clark has identified two main statistical profiles in rock, such as the flat side and the sharp side, or going with Everett, a more diatonic versus a more pentatonic rooted chord progression cluster. Such a definition of topics has a cognitive analog, since listeners have been shown to have different statistical profiles for harmonic expectation when primed with different genres, or in fact, when comparing the beginning, middle, or end of a piece, or even different positions within the measures of a 12-bar blues schemata. 2011 dissertation by Braden Hughes has showed that when primed with classical music, trained musicians are more sensitive to out-of-key progressions, hinting at what Walter Everett would call the more conservative cluster of chord progressions. Harmonic rhythm plays a significant role in expectations, and I will use this as part of my tokenization. Furthermore, listeners tend to expect recurring chord patterns, such as those found in Viamonte, some sequence of 2 to 4 chords beginning and ending typically on the same chord that can repeat and form the basis for a riff or a section. And given different positions in a 12-bar blues schemata, when primed with this, listeners have different sets of expectations, such as the 5-4-1 turnaround being a different set of expectations for things to happen versus the beginning. So now I'll describe the corpus that I use in these experiments, which is the McGill Billboard corpus. It contains hand-transcribed annotations made by graduate students just like me, and it contains bars, which contain chords. Chords are labeled by root and chord quality, and the corpus also contains sectional annotations such as introduction, verse, chorus, and timestamps within the original audio files. Years are distributed approximately uniformly across the corpus. However, due to sampling issues, the result tends to cluster around the late 1970s, as you can see in the following graph. I wrote a custom parser that converts these Billboard annotations to CSV and extracts metric information, which I will use as part of feature extraction. I normalize the corpus by transposing all songs to C major, and each token consists of the starting beat, the duration, the transposed chord root, and the chord quality. To simplify and regularize the corpus, I selected a subset of songs such that the meter was in 3/4 or 4/4, with no significant changes in meter throughout the song. After this thresholding process, 876 songs remained. So now I'll move on to the data representation and pre-processing, which is to say, given these chord tokens, how can we create chord progression tokens such that they are informative about musical styles and do not represent too much prior information in the sense of music theorists dictating what kind of chord should co-occur. I am motivated by the underlying assumption/observation that the amount of information conveyed by harmony is not necessarily constant at any point, which is to say that a rare chord might have the same entropy as a 4 to 8 bar chord progression that is incredibly common. And I seek to capture this during my tokenization scheme. To this end, I advanced the bar-gram model. I call it the bar-gram model as it is motivated by n-grams, except n is dictated by however many chords sum to one measure of music. I treat each measure as a token, containing the aggregation of some number of previously extracted chord tokens with labeled rhythmic positions within the measure, so that the same chord progression in different rhythmic realizations creates different tokens. The second step is to perform collocation detection to identify chord progressions between 1 and 4 bars in length that occur frequently within the corpus. The result is that long stretches, 4 to 8 bar stretches of the tonic chord, being very predictable, create single tokens, whereas rare chords do not tend to co-occur in collocations, and chord progressions consisting of some number of bars of moderately frequent chords co-occur into 2, 4, generally not 3 bar collocations. And I use these as a building block to create a topic model that describes musical style, musical genre, not just musical syntax. I form collocations based on the following algorithm. I threshold them based on the probability of tokens co-occurring within a document versus the probability of the two tokens co-occurring independently. I threshold based on 5 minimum occurrences of each collocation. And after collocations are extracted, I threshold the corpus once more, removing tokens that do not appear in 3 or more documents, which is to say songs, or 9 or more times overall. And at this step, I also threshold out bars or chord progressions that contain silence. I do so after collocation detection to avoid truncation, which would bring together chords that are not related. And here are some of the bargrams. If one looks at single bargrams, the most common are bars that contain single chords, most typically common diatonic chords. However, when one moves to bar bigrams or beyond, one finds in the top 10 collocations of chords that tend to have some functional meaning, 1-4, 4-5, 5-1, or 2 chord stretches of the same chord. But moving further down the frequency list, one finds tokens that are complete functional 2 to 4 chord progressions that indicate some level of musical style, such as the C major, B flat major on the one hand, with the F, G, C on the other hand, the flat side versus sharp side distinction. For the final models, I performed only 2 rounds of collocation detection, resulting in a maximum of 4 bar length and a final vocabulary size of 615 tokens. The final step in this is taking into account PMI, or pointwise mutual information, very similar to the collocation detection algorithm, but using a 3-term sliding window to indicate co-occurrence within a section of a song rather than co-occurrence within a song entirely. I also use PMI both to evaluate the resultant topics, which has been shown to have a very high correlation with human perception of semantic coherence in natural language topics, and to advance a new model of LDA, which uses PMI to regularize topics via structured priors, where the PMI matrix is used as a quadratic form to shrink the topic word probability vectors so that words with higher PMI tend to co-occur in topics. And here's an example of some of these topics. This is a graph of the PMI scores for both regular LDA and the PMI regularized model. A peak for the PMI model is shown at around 16 topics, which I will display the results of, since it is both very coherent, as seen in the graph, and is not a large amount of topics, so it is good for human understanding. First topic, compared to the PMI value mean of about 4.5, is not very coherent, although it has some minor level of coherence, which can be seen in that it has a lot of ninth chords that tend to co-occur. Although compared to the next topic, which is all power chords, and to top that off, power chords that are rooted on C, E flat, F, G on the minor pentatonic scale, the Amantes topic, this is a much higher PMI score and is much more coherent for human understanding. The next topic is a certain subset of diatonic chord progressions that do not end on root position tonic chords. Some element of a lack of closure is here, and it turns out this topic is actually correlated with medial function in songs, such as pre-chorus function or bridge function, rather than verse and chorus, which tends to have more root position chords and more closure. Many of the topics are aggregations of diatonic chords, such as this one, which is all 2-bar harmonic rhythm, mostly tonic, dominant, subdominant, submediant progressions. Interestingly, 3/4 is its own topic with an extremely high PMI, which is one downside of topic models, in that things that are a small subset of the corpus, generally in natural language, things that are Spanish in the mainly English corpus, the most frequent elements of that language tend to co-occur in one topic. Other topics include a flat side topic, a slightly jazzy extended chord topic. This is a blues topic, which includes the 5/4-1 turnaround, and many of the other topics are mainly diatonic aggregations, a diatonic leftover topic with a very low PMI. Similarly, this one generally has root progressions between chords that are a second apart, which is quite interesting as a single topic, since it is more of a medial role than progressions that evoke a sense of closure, or this, which contains mostly minor chords and is more used in slower, more atmospheric songs. I apologize about that. And more diatonic leftover topics. And I used these topics to predict structural schemata in songs. I trained a random forest classifier with 100 trees using tenfold cross-validation on 4 labels that occurred in the Billboard corpus. And the mean success rate over this cross-validation was slightly over 50%, which is better than chance, which for these unevenly distributed labels was in the high 30s. Bridge and pre-chorus are correctly identified in most cases, hinting at very distinct topical content, whereas verses and choruses tend to be more similar. And the classifier had the most difficulty predicting the chorus label, since, as some theorists have hypothesized, and as I do, chorus is it's very predictable to maximize listener entrainment and listener enjoyment, so perhaps that is why it is the most evenly distributed topical content. And here's the confusion matrix for that, showing good performance for bridge, pre-chorus, and not better than chance for chorus. And the final experiment was a year prediction experiment, similarly random forest, 100 trees, with tenfold cross-validation. 2 models were used, with the corpus year sorted into 5 and 11 bins. And here the models did perform significantly better than chance, although not particularly well. And looking at the confusion matrix for this yields very interesting results. We can see some clusters of songs that tend to be more identifiable than others, such as 1988 to 1991, which Matthias Mauch, in his topic modeling study, identified as one of the important change points for topical content in music. Thank you.
Why is 91 apparently this change?
Well, as Temperley and de Klerk mentioned in their corpus study, this is when a lot of genres started shifting. Rap decided to come to the forefront, which created a lot more songs that did not have traditional harmonic content, as well as the decline in musical genres that were more prevalent during the 70s and 80s. And Mauch et al. Decided this not based on musicological reasoning, but rather a change in the topical content of songs, one of which was the timbral topic that they identified as songs containing speech becoming more prevalent, which would match up with the Temperley and de Klerk analysis of that.
So you transposed everything into C major, and I to understand by that you use no minor tonics, like no songs with minor?
Songs with minor were transposed to be in C. C was just the root for this.
Minor.
So things that are minor are now rooted in C rather than rooted in A minor, which would happen if I transposed them the other way. Since I separate root and quality as different parts of the tokens in the model.
Have you looked at the structural similarity between certain topics? Some topics statistically are obviously very much more different from others, and whether that relates in some way to their use within certain sections within songs?
Let's see. The topic that had more medial function chords, I believe was the third topic identified, was more common in bridge and pre-chorus sections. The covariance matrix for the topics shows very little correlation between the topics, indicating a rather good fit of the model. I don't believe any R values were over 0.1 for that. What was the other part of your question?
Just the relationship of the structural similarity between some of the topics and the way they may be overlapped in certain parts of songs.
What do you mean structural similarity
Well,
between
just literally
topics?
how
I'm not defining a similarity metric for topics other than co-occurrence.
That's an interesting point, because you're talking about functions. Some chords, you've got ones and fours,
right,
close relationship to each other. So from a functional point of view, some topics are going to have more overlap than others.
Right.
And does that relate to the way those map onto different parts of songs? So if you've got more overlap in terms of the functional similarity between topics, do you find that?
This would be an interesting investigation, although I don't know of a good purely quantitative metric of chord function, since a lot of those theories are so subjective. but that would be interesting. I did try a similar topic modeling experiment separating chord roots from chord quality, although I did not find any coherent results since the vocabulary size for both was reduced significantly. But there are quite a lot of diatonic topics, and some of the lower PMI topics tend to be more frequent in every section, since they are more or less the aggregation of things that don't tend to co-occur strongly and are just like the tokens you'd use in constructing a simple Markov chain model of music.
Thank you again, Dakota.